Hey Ian, how's it going?
It's pretty good.
How's life?
Sort of weird. I'm looking at this Applied Texas thing for the 2021 freshman admissions for like Texas schools. And then, but it says for the essay thing, the deadline to submit essays for this application is December 1st, 2018.
Oops.
They
That's like,
probably didn't even update like the page. They probably just copy and pasted what it was like what it had for 2018.
yeah, totally.
Because this is like a lot of stuff for them to just write out every year.
Yeah.
It's like the same prompt from like 2 years ago.
Yeah, I doubt they change a lot of that frequently. That's probably a lot of work because they don't want to do it. How are y'all doing?
Good. How are you?
Doing okay. How's the first full day of Zoom meetings? Did it feel really long? It's also that day where everyone just like goes over their class, and it's probably kind of not super exciting. I mean, not that school's necessarily exciting, but all right. Oops. All right. It looks like we're all here. All right. Today we are going to go ahead and start our notes. So if you want, you can download. I basically put just the slides of the presentation in Google Classroom. You can, if you like to print them out and do them by hand, I would print on the printer. You can print like 6 to a page, and that way you're not printing like, I don't know, it's like 20 pages or something like that. Or you can annotate it on an iPad, or you can just take notes on the paper. It doesn't really matter. A lot of this stuff should be hopefully pretty easy as we start out. And we're basically talking about vectors today. A lot of the course is based on vectors. once you pass 2 dimensions, vectors are one of the better ways to kind of express how something is behaving, because in 2 dimensions, it's really easy to do like X and Y. In 3 dimensions, those two, or just using cardinal directions, don't give as specific a direction and movement as we usually like. So we tend to use vectors a lot. If you're in Physics C, a lot of this will overlap with what you guys do in Physics C. The notation Mr. Masage may use is a little different sometimes. You're welcome to use what you use in physics notation-wise in here as well. It doesn't really matter to me. I wouldn't do the same in his class unless he tells you that's okay, because he may be more of a stickler on that stuff. So I am going to share here and see if I can, it hasn't worked great yet. See if this will work better here. All right, let me see. I'm gonna do this. Okay, and so hopefully you can see the notes here. It says vectors in a plane, all that stuff. So you guys see that? Okay, so let me see if I can make it work. It's not moving on my iPad. Oh, there we go. Okay, so basically when I think of vectors, I think of Despicable Me. If you guys ever saw Despicable Me, I think it was the first one. It might have been the second one. One of the bad guys was named Vector, and he was like, it has direction and magnitude. Well, that's the definition of a vector, is it's a quantity having direction and magnitude. And so we generally represent it by a directed line segment. And is it appearing? Oh no, it's not gonna appear. Did anything appear on your screen, like drawing? Oh, there it is. Okay, a directed line segment. So if you think back to geometry, this looks similar to a ray. The difference is a ray would keep going where that arrowhead is. That's generally with a ray considered to be going on forever. With a vector, it stops. That's just indicating the direction it's going. It's not actually keep on going that direction forever. Parts of a vector, let me see if this shows up again. We have an initial point. Okay, so labeled like any other point, A, B, C, whatever. We have a terminal point. And so then we would normally call this vector AB. Sometimes, again, a lot of correlation with geometry, if you think back, like there's sometimes like line L instead of line AB. They could name it with a little lowercase l. We can do the same thing with vectors, which we do typically a lot, is say this is vector V with a little lowercase v. Okay, and I would say this is ways we would note it with like handwriting. Meaning when you take notes, when you do homework, when you do a test or whatever, you would generally write it one of those 2 ways. Typed, meaning in a textbook, or if you were typing homework answers or whatever, a lot of times they'll do bold, which you can't really indicate with handwriting very well. But if you see like a bold V, or a bold letter or whatever, they're talking about a vector. So yeah, generally handwriting, you don't want to do it that way. You want to use symbols, and just be careful. Symbols do matter. In college level math, you start mixing things. So I keep referring back to geometry, but geometry is part of a lot of courses. And when we see AB, that can mean the length. If you write it this way, it can mean a line segment. If you write it that way, it can mean a line if you write it that way. So we want to make sure that we're doing correct notation so that it's not confusing when you start kind of putting things together. So there I put it by hand, AB or vector V, in typed print, a bold V. So you could even tell, it's hard to even tell it's bold there, let alone if you were to try and do that by hand. Length or magnitude is denoted with kind of two absolute value bars. So that's usually how we write magnitude. This is a number, or what we call a scalar, which just means it's a number. It's not a vector. It's a length, so it'll be like 10 units or whatever length. Vectors of the same magnitude and direction are called equivalent. So if we have vector V, and we have vector U, and if they have the same length and the same direction, they're called equivalent because location is not really one of the main quantities associated with a vector. Where it's located doesn't really matter. Its length and direction do. So in most of our, like when we start working problems and stuff like that, they can be interchanged with each other. It doesn't really matter the location. As long as they have the same magnitude and direction, they're typically considered equivalent. Okay, as far as component, oh, I think I skipped something then. I think I skipped one thing here. It's not on here, but direction is also an important number. So we have magnitude there. Direction, if you pictured the coordinate plane being here, just like with the unit circle, direction is typically an angle from the positive x-axis counterclockwise. So just like we did with the unit circle, mathematically, that's how we usually talk about direction. So it might be 20 degrees. We're saying then it's 20 degrees or 180 degrees or whatever. If it's specified in another way, it can be. Sometimes I use north, south, east, west if you're talking about objects actually traveling or whatever. But typically we talk about it as an angle from the positive x-axis counterclockwise unless it's specified otherwise. Okay. Component form of a vector, as we start working problems, we tend to look at the components of a vector. Components just being how far in the x direction it moves and how far in the y. So like if we have a vector, we're basically saying how far over and how far up. If we're at the origin, the components are super easy because it's literally whatever the terminal point is, right? How far over we moved and how far up we moved. That literally is the coordinate x1, y1. Well, then in component form, if this is vector v, we would say it's x1, y1. We typically use little caret symbols because if we put parentheses, it can be mistaken for a point. Some books do use parentheses. I've been in classes that use parentheses, and therefore sometimes I accidentally use them. They're somewhat interchangeable. I prefer the caret because it's distinct from a coordinate point. If it's not at the origin, remember that that doesn't really matter, but we're still looking for this distance that we've moved here and this distance that we've moved here. And it's still super easy. If this is x2, y2, and x1, y1, that distance is really easy to find, right? We just subtract. If we subtract the x's, we'll get the distance we moved in the x direction. If we subtract the y's, we'll get the distance we moved in the y direction. And we just subtract terminal minus initial. Because remember, direction is going to matter. If you do initial minus terminal, it'll be going the other direction. So you do x2 minus x1 and y2 minus y1. That'll give you your components no matter what, no matter where it is. Okay, the 0 vector is, I mean, a pretty simple concept. It's like thinking of 0 in math and any other math class. It'll look like a point, right? Because it has no horizontal or vertical components. So our 0 vector has components 0 and 0. But just like arithmetic, 0 or algebra or anything else, 0 will come up as things that we use or want to talk about. So the 0 vector is the same idea. We even can write it as just a 0 with the vector symbol over it. And that just means the 0 vector. Its location, again, doesn't really matter. So it could be anywhere on the page. Don't generally graph it because it's not going to have anything to it. Oops, sorry. Okay. As far as vector operations go, let's say we have vector v that has components v1 and v2, and vector u with components u1 and u2. The sum is really simple. If I want to add the vectors together, I just add their x components and I add their y components. If I want to do a scalar multiple, scalar just being a number. So if I want to like multiply a vector by 2, well, then I'm just going to multiply each component by that scalar. And then you can use that exact same idea to take the negative of a vector will just be the negative of every, you multiply each component by a -1. Okay, and so a lot of the stuff in this lesson should be pretty intuitive, like stuff that you would either know, you've seen before, or probably things you just do. If you want to take a difference, you have 2 ways of doing that. You could literally just subtract the components. So I could take u1 minus v1 and u2 minus v2. Or you could even think of it, which this is how I think of it geometrically, is pair that with some of the stuff that came before, and you're just adding a -v. Okay, subtraction's not its own different thing. You're just adding a negative there, just like with arithmetic again. Okay, and then the magnitude of u. If we think of u having gone u1 this way and u2 this way, magnitude is really easy to find length. We're just doing the distance formula or Pythagorean theorem, the same thing. We're just taking the square root of u1 squared plus u2 squared. Okay, it's Pythagorean theorem. To get the length of u, we'll just square the components and add them together and then take the square root. All right. We usually talk about vectors algebraically. Like that's when we're solving a problem, we use algebraic notation, right? Things we can plug into formulas and stuff like that. But sometimes we want to think about them geometrically, which is more visual. I will say as we go farther into the course, that only really is very helpful 2 and 3 dimensions, right? You can picture in 2 and 3D. You can't picture something in 5D very easily. So geometrically, we can kind of come up with ways to visualize the things we're learning in 2D and 3D. Those formulas still work in higher dimensions, but the visual doesn't really work anymore. But we did this back in, again, geometry pre-cal. If you have u and you have v, and we want to add them together, we put them head to tail, basically terminal point to initial point. And geometrically, analytically, what we just did, we just added the components. If we do it geometrically, you put them head to tail, the third side is then u plus v. It's called the resultant. Okay, so you should also, I mean, you guys have seen that before. All you do to add geometrically is put them head to tail. You get the same thing as what we just saw analytically. Just adding the components together, you'll get that same vector. Geometrically, it can be nice to kind of picture what's happening, but we tend to do it a lot of analytic ways. The difference, you could do u minus v or u plus a negative v, and I think I have that in here somewhere later. Okay, scalar multiples. You should realize that scalar multiples will only do two things: either change the magnitude or change to the opposite direction. A scalar multiple will never go like v and then all of a sudden have it go this way. Okay, that can't happen. It's either going to make it go a different magnitude but the same direction, or the opposite direction, meaning literally the opposite way. So the magnitude will increase. If you think about it, it's not just when c is greater than 1, which is what a lot of people first think here. That'll increase the magnitude. If c is 5, it'll be 5 times as long. If c is 7.3, it'll be 7.3 times as long. But also, if it's less than -1, the magnitude will increase as well. If you have a -5, that's going to make it 5 times as long. It'll just be going a different direction. So it'll increase when the absolute value of c is greater than 1. It'll decrease when you have things like fractions and decimals between 1 and -1. Right? If you have like a half times v, you'll get something half the length. If you have -1/3, it'll be a third the length and go the opposite direction. So we maintain the same direction when c is positive and go the opposite direction when c is negative. So like if we have v, 1/2 v will go the same direction but be half the length. -3v will be 3 times as long and go the opposite direction. Okay, so you'll basically get a bunch of parallel vectors with different lengths and things like that. When you do scalar multiples, it won't all of a sudden like make it go some totally weird direction. All right. Oh yeah, this is what I was saying earlier. Vector subtraction you could think of as adding a scalar multiple of -1. So just like we were saying picture-wise, if I have u and v, adding, I think of head to tail. If I take v and I write it as a -v, meaning I just go the opposite direction, don't change the length, u minus v would be placing u and -v head to tail. And then this would be u plus -v or u minus v. So geometrically, that's usually how I would picture subtracting, because otherwise you're trying to put them head to head or tail to tail and make sure you're doing it in the right order. Geometrically, I usually think of adding a negative. But again, analytically, you don't have to think about it at all. You just subtract or whatever. So this is only if you're trying to picture it or draw it or whatever. Okay. Properties. Basically, every section we go over some properties of whatever we're talking about. Main idea of learning these properties is with math, you want kind of hard, fast rules. When you say this works, you want it to work for everything. You don't want it to work some of the times, but not others, or only when this happens. You want it to work all the time. So we come up with these properties that are things we know are rules for no matter what the vectors are. And then you can do things like proofs, create new formulas, all these types of things. You need kind of a set of rules to work by. So luckily, these ones are exactly what the same rules that you guys learned probably in elementary school with arithmetic. As we add operations and things, sometimes they're not so intuitive, so they'll be more important. These ones are pretty easy, right? We have the commutative property. U plus V is the same as V plus U. Order doesn't matter when you're adding the vectors. Okay, and the associative property is true as well. U plus V plus W. It doesn't matter which ones you add first, right? I could add V plus W, then U. I could add U plus V, then W. Associative property is true here as well. You can group however you want with addition. Just like with arithmetic, U plus the 0 vector is just going to give you U. Adding the 0 vector doesn't do anything. And just like arithmetic, if I take vector U and I add its negative, I will get the 0 vector. The associative property is true with scalar multiplication as well. So if I want to take C times D times vector U, I could multiply D times vector U, then C. Or I could multiply C and D together, then multiply times vector U. That's not going to change the result. There's several distributive properties. If I take C plus D and then multiply by U, it's the same as taking C times U plus D times U. If I take C times the sum of two vectors, U plus V, again, distributive property works here, C times U plus C times V. And then just like arithmetic, if I take the scalar 1 times the vector U, I get the vector U. And if I take the scalar 0 times the vector U, I get the vector 0. And that's the only thing that gets a little confusing for people in this early stuff with vectors is a scalar times a vector gives a vector. So 0 times U is not the number 0, it's still a vector. It'll still have the two components. You'll have done 0 times whatever the first one is and 0 times whatever the second one is. And so you'll have 0, 0 still. You still have a vector, which is only going to really matter as we're doing operations. I can add vectors, I can add numbers, but I can't add numbers to vectors. It doesn't work. Okay. So we don't do a ton of proofs in here, but I'll sometimes just show some proofs. I don't really, some of the homework has them, the tests never have them, but sometimes I do them just to kind of show that why something is true instead of just kind of like memorizing it. So notice CV would be CV1 times and then CV2. And so we went to find the magnitude of that. Remember that we take the square root of the squares added together, so we do Pythagorean theorem. And then we could further simplify that by factoring out a c squared. And then because of, again, arithmetic, what we kind of know about square roots, I can take the square root of that c squared, that's a perfect square, and I get c times the square root of v1 squared plus v2 squared. And notice that's just the same as c times the magnitude of v. That's what we would have gotten if we had just factored the c out and found the magnitude. This is helpful in certain formulas, things like that, but also just in mental math. Say we wanted to find the magnitude of 4824. Some of you may be very good with squaring things like larger numbers. But this is the same as 24 times the magnitude of 2, 1, which that's pretty easy to do in your head. Let's find the magnitude of 2, 1 is the square root of 5 versus finding the magnitude of 48, 24. So the square root of 48 squared plus 24 squared, which I can't do in my head. So it helps with like mental math, with cleaning up your work, with simplifying, stuff like that. This property that you could factor out a common factor, then find the magnitude, and you don't have as large of numbers and weird stuff to deal with. Am I frozen? Uh-oh, you guys aren't moving, which makes me feel like maybe I'm not moving. Oh, I'm back. Sorry. I don't know what happened. The internet went down or something. Okay, so go back to what I was just doing. Okay, so did everyone finish that one? Everyone good? Okay, so with unit vectors, these show up in a lot of formulas. Main reason is if you plug any vector you want into a formula, it's very hard to make the formula work for all vectors because the length could be wildly different. One vector may be 2,000 miles long and one vector be 2 inches long, and it's hard to make a formula work for any of those things. So we use a lot of unit vectors. All a unit vector is it's a vector that's going in the same direction as the one we're interested in, but has a length of 1. So for example, we may have V be this really long vector. We might want U, the unit vector, in the same direction. Would be just another vector, just it's 1 unit long as opposed to, it could be thousands of units long, V, and we want it to be 1 unit long. That's going to be a really important idea later, is we're more interested in the direction than the magnitude in a formula or something like that. And we use a lot of unit vectors then to make those formulas work correctly. So all we do is we call it a unit vector in the direction of V. To find that, it's called the normalization as well. I don't tend to use that term, but a lot of books and stuff do. All we do is we take the magnitude of V, and we divide V by its own length. And that'll give us something with a length of 1, or sometimes you'd see it 1 over the magnitude of V times the vector V. Okay, remembering that this part, this is a scalar. It's just a number. So it might end up being half if the length of V was 2. Taking half of it will make the length 1, or whatever. So for example, if V was 2, 3, we could find the magnitude of V is the square root of 2 squared plus 3 squared, so the square root of 13. Right, then U would be 1 over the square root of 13 times 2, 3. And now if we went ahead and found the magnitude of that thing, you did 2 over square root of 13 squared and 3 over square root of 13 squared, add them together, take the square root. It'll have a unit, 1 unit length, but it'll be going in the same direction because notice it's a multiple of V. As far as simplification goes, you should try to simplify as much as you can in this class. Last year, the only reason we never simplified was an AP testing strategy. So you should still be simplifying. This is simplified enough. Okay, you could also write this as 2 over square root of 13, 3 over square root of 13. Or if you wanted to rationalize the denominators, 2 square root of 13 over 13 and 3 square root of 13 over 13. You don't have to rationalize. I've never been in a college class where they made you rationalize the denominator. But don't leave something like 1 over square root of 16 times 4, 8. Okay, to me, that's something you could easily simplify. 1/4 times 4/8 is 1/2. Okay, this should really be your answer. Don't do stuff like this. Okay, so you guys should be trying to simplify where you can, but you can leave square roots in your answer if they're not perfect squares. You can leave fractions if they can't be simplified. So like 1/3 is fine, but 6/3, I would not like to see that. So stuff like that, okay? All right. There is an inequality that can be shown with triangles. This one also comes up a fair amount in different places. There's multiple ways to prove it. You can prove it analytically. We're just going to show it geometrically really quickly. Is you can't break up a magnitude like this. So people are tempted to want to oversimplify things. The magnitude of u plus v won't be the same as the magnitude of u plus the magnitude of v most of the time. Because again, if we think geometrically, this is what that would look like. This is u plus v. And remember in, again, geometry, the sum of two sides of a triangle will be greater than the third side. Okay, technically this can be equal sometimes only when u and v are the same direction, right? The equal part would be if this was u and this was v, then yes, u plus v will be the same length. But if they're going in even slightly different directions, the magnitude of u and the magnitude of v will add up to be greater than the magnitude of u plus v. And that's geometrically, we can show that pretty easily. Analytically, we'll actually see that later as well. Okay. Standard unit vectors, again, if you're in physics, this is one of the things you'll see and use in physics. And in any higher level math, we tend to use this more than component form. Are these things called standard unit vectors? So notice they're unit vectors. They're 1 unit long. And they're basically 1 unit going in the x direction and 1 unit going in the y direction. And those are really great ones to use because we can express any vector as a combination of those two. All right, so if I take vector v and it's got 2 random components, no matter what they are, I can easily express those, as a combination of 1, 0, 0, 1, right? Just whatever that x component is times 1, 0, whatever that y component is times 0, 1, add them together. So this leads to what's called standard unit form, which is written this way. This and this are the same thing. Okay, they're just 2 ways of writing vectors. Standard unit form is most common in higher level math. So like, if you look in the textbook, they'll start using that more frequently. Like physics will tend to use that. Other math will tend to use that. I'm fine if you want to use component form, but you need to understand both. So if you see one, you should be able to understand it, even if it's not the one you prefer to use. It's super, super easy. If you have your components are -3, 4, that's just -3i plus 4j. Okay, and this is one in physics. They'll do I hat, j hat is what they call it. Those are the same thing. And it doesn't matter to me what you use. Sage will want you to use those. Yeah, that's just, you're just multiplying -3 times 1, 0, 4 times 0, 1, adding them together, and that gives you that one up there. All right. If you're in a real world situation, you probably don't have the components of a vector. You have the magnitude and direction. So if you're taking measurements, doing an experiment, whatever, you might know the magnitude and direction. But then to do math, we generally want the components. So you want to make sure if you see a magnitude and direction that you can kind of go backwards and get those components so that you can start to kind of do math stuff on it. So say our vector is going 3 units at negative pi over 6 radians. So that would be like down here. This is pi over 6, 3 units long. And now we want this length and this length to get its components. You could use trig, right? If we have the hypotenuse, we could say, well, the sine of pi over 6 should be y over 3, and the cosine of pi over 6 should be x over 3, and we could solve that way. Since it's a unit circle value, we could also just use the unit circle. Right, if we were on the unit circle, this would be root 3 over 2, negative 1/2, knowing that that's a magnitude of 1. So if we want a magnitude of 3, we just multiply by 3. You'd get the same thing either way, right? You could use trig, you could use the unit circle. In component form, it'll be 3 root 3 over 2, negative 3 over 2. If we wanted it in its standard vector form, 3 root 3 over 2i plus, well, minus 3 over 2j. And again, unless it specifies, I don't care which form you generally use, you can kind of choose that yourself. But you want to make sure you kind of understand, this is all based on trig. So you can use simple trigonometry stuff to get what's missing if you have parts of the vector but not other parts and you need it. Usually Pythagorean theorem and other trig stuff will get you there. All right, vectors is a force. Often we use vectors to describe forces because the main thing with a force would be a magnitude and a direction. So if you're pushing or pulling or lifting or dropping or something is happening, there's a force involved, like a magnitude of a force involved, and there's a direction. So like if you had a weight, well then gravity is pulling down. The magnitude would be that 1 kilogram. The direction would be, you know, negative pi over 2 radians or whatever. We're going straight down. And then you can pair up forces and use things like vector addition and subtraction to figure out how that's affecting a situation. And so you guys did this in pre-cal. You may have done it even in pre-AP geometry, where you had situations where, oh, whoops, I changed the picture, but I didn't change the words. I used to have the boats pushing the other boat, and then people were really concerned that why would a tugboat be pushing and not pulling or whatever. So I just changed it. All right, so say we have these 2 boats. They're pulling a larger boat, the ocean liner. And we kind of want to know what's the resultant force on the ocean liner if the tugboats are both pulling 400 pounds of force at this angle. A simplistic answer would say 800 pounds. If they're both pulling 400 pounds, then there's 800 pounds. But that's not happening because remember, if the tugboats are pulling at an angle like they are in the picture, it means part of the force that they're pulling with is going this way, but part of it's also pulling out, right? It's got 2 different kind of forces because of the angle. It's some of that 400 pounds is not going in this direction, which is what we're really concerned with. So again, geometrically, we could line up the tugboats. And this would be the one we're looking for. If this is tugboat 1 and tugboat 2, this would be our resultant force. And we're back again. Where did my binder. Okay, we're almost out of time anyway, but so you could line them up head to tail. Obviously the picture would no longer match the situation, but that's how you could solve it geometrically, is you'd shift things around. Keep the directions the same and stuff, but you would just move them on the page to solve it geometrically. We would typically do it analytically. So I would come up with a vector for tugboat 1. And I usually think of it as doing a unit vector going in that direction. So notice it's going 20 degrees from the positive x-axis counterclockwise. That's exact direction we want. A unit vector then is just cosine 20, sine 20, right? Think of the unit circle. That'll give me a unit vector going in that same direction as the tugboat. All I then have to do is multiply by the magnitude that I want. And so that's an easy way to come up with a vector for that first tugboat is 400 times a unit vector going in the same direction. Pretty much with that, if I have an angle, I just use the unit circle. It will always be a unit vector going in that angle. Take tugboat 2 is very similar, but notice it's not 20 degrees counterclockwise from the x-axis, it's 20 degrees clockwise. So the only thing that would change there is we wouldn't want to use 20. We would either want to use 340 or negative 20, which would change the sign value, right? It would make that one a negative number. So it would affect it. So you want to make sure you're kind of paying attention to, just because they call it 20 degrees, if it's going a different direction, 20 degrees, you need to take that into account. The resultant, I would then just add T1 plus T2. Okay, and you could use a calculator here. If it's 20 degrees, that's not a memorized unit circle value, so I wouldn't expect you to just like pull that out of your head. But you could either, if it's non-calculator, leave it with the cosine 20, sine 20 in it, or you could use a calculator or whatever if you have that. Okay, and then that would give you a resultant force. You find the magnitude, and that would be kind of the force with which the boat is actually being pulled forward. The direction is kind of obvious here since they're at the exact same angle with the exact same force. The direction's going to be 0 in this case. But if they were at different angles or different forces, it may cause the ocean liner to go at a weird direction. Okay, and then the other thing, and we may or may not totally finish, and if we don't finish, I'll finish it tomorrow, but in navigation, we don't generally, so like aviation, they don't use mathematical direction. They use north, south, things like that. So in bearing, it's usually measured from a north-south line. So we would literally have north-south, and this would be things moving. And so if something was over here, they would choose the acute angle between either the north or the south. And in this case, obviously the acute angle would be here. Okay, if the vector was going here, they would choose this angle from the north. So you would see things like north 20 degrees west, or south 60 degrees east. Okay, meaning from the south, we went 60 degrees to the east, or from the north, we went 20 degrees to the west. So some things will use that. Air navigation is always from the north, clockwise. So they will always choose to measure this way in air navigation. So they did not choose to use the mathematical standard, which is fine. So just be aware of that. I'm not a huge stickler on which one you choose to use. If I don't specify that it's air navigation or bearing or something like that, I'm using the math one from the positive x-axis around. All of our formulas are from the positive x-axis around. If it's given in this notation, you would have to figure out what is the equivalent angle from the positive x-axis going around before plugging it into a math formula, or it's not going to work. Okay, or same here, if this was a vector, you would have to figure out what is the equivalent positive x-axis going around before subbing it into some formula we've come up with. Okay, and then the last thing on here, which I won't finish, is those airplane problems. You guys probably had a ton of these in pre-cal, where you have an airplane traveling at a fixed altitude with 500 miles per hour, bearing of 330. So remember, that's going to be telling you that this is 330 degrees, and this would be the plane's vector. 500 miles per hour would be the magnitude. And then at a certain point, you encounter wind. Velocity 70, which again would be the magnitude, direction north 45 degrees east. So that would be this way. North 45 degrees east would be saying start north, go 45 degrees to the east, and this would be your wind. And so it's saying basically, what is the wind going to be doing to the plane's course? Okay, what's its resultant speed and direction? Well, you would want to come up with a vector for the plane, which again, if this thing is 330, we would want to be able to come up with this before trying to use like the unit circle to come up with a unit vector. But if that thing's 330, this is 30. And so the bigger one would be 30 plus 90 is 120. Right, so our plane would be 500 times a cosine, 120, sine 120. So before kind of using that unit circle, we need to make sure we have the angle from the positive x-axis. Our wind would be 70. And then again, if that's 45 degrees here, we need this angle, which happens to also be 45 degrees. So then if I add the plane plus the wind, if I find its magnitude, that's the resultant speed. That's basically what the wind is doing to the speed of my plane. If I find the direction of that sum, the new angle, that's its new direction. Okay, the wind is going to cause the plane to start moving unless it alters its course to compensate for that. All right, we are out of time, but we actually made it to the end of the slides with only losing connection twice. I will, post the video of this recording on Google Classroom if you missed anything or you need to go back to anything. Hopefully that one's not too bad. And you guys have a good rest of your day because I went 2 minutes over, so I'm going to let you guys go. Bye, guys.
Thank you, Mr. Smith.
Thank you, Mr. Smith.
Thank you.
Have a good day.